All right, our next notes are on inverse functions. This is section 1-6 in your textbook. And we'll jump right in. Our first example says find the inverse of this function here. Now, inverses. So you've been working with inverses ever since, probably first grade. So in first grade, you learned how to add and subtract. If you add 5 to something and subtract 5 from that same thing, you get back where you started. Adding 5, subtracting 5, those are inverse operations. Multiplication and division are inverse operations. Inverse functions work the same kind of way. So you have these inverse operations going on, but really the easiest way to define an inverse function is it's a function where the x and y are switched around. So for example, if you had the point, let's say 2 comma 5, the inverse of this point would be 5 comma 2. So even a point can have an inverse. Thinking of it that way, that's probably the easiest way to think of what an inverse is all about. Let's get that out of there. Let's jump in and find the inverse of this function. Well, I'm just going to jot down the 2 steps to find an inverse. So first step is to switch the x and y. Okay, so just like that point 2 comma 5, you switch the x and y, you've got the inverse. But then we need to simplify a little bit. So I'm going to put here solve for y. Now we're solving for our new y there. Okay, so here's our original function. Y equals 4x minus 1 all over 3. First step, switch x and y. So that gives us x equals 4y minus 1 all over 3. So there's your first step. Second step now, solve for y. I need this y by itself. Well, what do we get rid of first here? Let's see here. We've got y times 4 minus 1 divided by 3. Since the last thing we're doing is dividing by 3, that's the first thing we undo. So we do the inverse of divided by 3. We multiply by 3. So that gives us 3x equals 4y minus 1. Okay, y times 4 minus 1. Next thing we need to do is add 1 to both sides. That gives us 3x plus 1 equals 4y. And lastly, we need to divide everything by 4. So that gives us y equals 3x plus 1 all divided by 4. Now, the proper way to write this is to say the inverse function, the inverse of f of x, equals 3x plus 1 all divided by 4. Now, this notation here throws people off. That's not f to the negative 1 power. It's read the inverse of f of x, or the inverse function is 3x plus 1 over 4. Now let's just think about this in terms of our inverse operations. For your original function, you had your x times 4 minus 1 divided by 3. Think about all these inverse operations. Here's your x times 3 plus 1 divided by 4. So really it's just taking the operations that were happening in this first function and we're doing the inverse of all of those operations. That is an inverse function. Okay, well now that we know how to find an inverse, let's talk about those 2 functions. You don't need to write them down again because it's the exact same functions, but different kind of directions here. These directions say verify that that inverse function we found really is the inverse of this. So it's like saying prove that this new function is the inverse of this original. Now I know as soon as I say the word prove, you think back to your geometry days. Some of you do not like those days because you hated the idea of proofs. Well, this is not 2-column proofs. In fact, you will never ever write a 2-column proof again, even if you become a mathematician someday. 2-column proofs is really just a geometry idea, and they're really pretty worthless when it comes to algebra. So an algebraic proof, we need to somehow show that this second function, or as it's written this way, this first function is the inverse of this original function. Here's how we do that. Well, to do that, we have to think about our combinations, and guess what? If we can show this is true, then yes, these are inverse functions. F of the inverse of f of x is always going to be equal to just x. Now that looks complex, but here's what it means. It means take this function, plug it in for x in this function, And if the whole thing equals x in the end, then they are indeed inverses. And you might be thinking right now, this looks really, really complex. Bear with me. Watch this. So instead of writing 4x minus 1 over 3, I'm going to write 4 times all this stuff. And again, many of you are thinking, oh, this looks terrible, but look for a shortcut. What do you see that we can do here? Oh, check this out. We have times 4, we have divided by 4. Times 4 divided by 4, they're inverses, so we can simply ignore them. Then that gives us, ooh, we have a plus 1 and a minus 1. Those are inverses. Now look what's left. 3x over 3. Hey, this whole thing is equal to x. What looked complex is really relatively simple. So to verify two functions are inverses, take one, and actually you could take either one, plug it into the other one. If it all simplifies to x, then yes, they are inverses. Okay, so let's practice those same things. So again, here's where I'd like you to pause the video, try this out. I'm going to forge ahead, so we need to find the inverse and verify that it is the inverse. Okay, hopefully you've tried that out. To find the inverse, I need to think of this function, and we do two things. We switch x and y, and then we solve for this new y. So that'll give me x plus 5 equals 3y. Solving for y gives y equals x plus 5 over 3. And I'm just going to use the correct notation. The inverse of the function equals x plus 5 over 3. Now let's verify. I'll switch colors for this. So that means take the original function, plug this inverse right in here for x. So instead of writing 3x minus 5, I'm going to write 3 times x plus 5 over 3 minus 5. And if you did it correctly, you'll notice, hey, times 3 divided by 3, they're inverses. Plus 5 minus 5, they're inverses. So all we're left with is x. So that verifies, yes, this answer we got truly is the inverse of this original function. Okay, nice. All right, let's move on to another example. So now, instead of just finding an inverse, we are going to try to graph an inverse. Okay, and it's saying graph this function and its inverse. Well, the nice thing is, look at this original function, y equals 3x minus 5. Hey, is that what I had on the last page? Something like that. Well, to graph this, we know it's a line that goes down 5 units and has a slope of 3, or up 3, right 1. So I'm going to get as many points as I can fit on my graph paper here. And then I will connect these. I will try to connect these with a straight line that goes on forever. Okay. Now the second one is a little bit trickier, but let's just write it in a little bit different format. Sometimes people see these and they say, I don't know the shape of that graph. Well, let me write it a little differently. So I'm going to say y equals, I'm going to divide each part individually by 3, which might help you out. And you might say then, oh, it looks like something I know. It looks kind of like this, y equals 1/3 x plus 5/3. Hey, that's the equation of a linear function. So if we go up 5/3, which is 1 2/3, then from there go up 1 and 1 to the right 3. And we can continue to do that. We can also go in the other direction. And I'm going to connect those points, extend the line, and we're done. So question for all of you, let's think about this. If the original function is a line, is the inverse always a line? Yes, it is. And in fact, the shape of the original function and the shape of the new one are always related. Here's why. Let's think about what inverses are. Inverse means switch your x and y around. So if you have a point on your first function like 2, 1, you'll have a point on your second function, 1, 2, right there. Now, if you think of it that way, we can actually put a mirror right here at this diagonal, and any point on one side on one function is going to show up on the other side on the inverse function. So for example, this point here, they are mirror images of each other. That diagonal line that I put in there is actually the line y equals x, y equals 1x plus 0. So inverse functions are always reflected across this line. Now that's kind of handy because let's say we know how to graph this first one, but not necessarily the second one. Well, you can simply plot some mirror image points and get your graph of the second function. So let's take a look at a couple problems where that might come into play. So here's a function. It looks a lot like y equals x squared. Does this function have an inverse function? So let's think about this, and I'm going to make this picture a little bit bigger here. Does this have an inverse function? Well, we know inverse functions are reflected across this line, which is y equals x. So if we reflect some points across here, well, there are some points right on there, but then there's some other ones that get reflected across, and we get a new function. It's going to be the exact same kind of curve, just reflected across there. Now, let me ask you, does this function have an inverse function? That's the key word. So let me ask you this. Is that new curve I just drew a function? The answer is no. I believe in your Algebra 2 days you should have learned the vertical line test. This graph, this curve, fails the vertical line test, so this function does not have an inverse function. It looks like it has an inverse. Is that inverse a function? No, so this function does not have an inverse function. Now that same idea is going to come into play with our last example on here. So let's see if we can switch to another page here. Okay, let's try this way. Okay, find the inverse of this function. Okay, final example of this set of notes. We need to find the inverse of this function. So we know how to find an inverse. We can switch our x and y around. So I'm going to say x equals the square root of y minus 2. And then, okay, we've got this y minus 2, take the square root. Let's square both sides. We know square and square root are inverses, so that gives us x squared equals y minus 2. And then we can add 2 to both sides, which gives us y equals x squared plus 2. Or we can write this as the inverse of f of x equals x squared plus 2. Seems pretty straightforward, seems pretty simple until we go to try to graph these two functions. And I'm just going to tell you, grab a calculator and graph these if you wish, but this first function, here's what a square root function looks like. So it's shifted over 2 units, and it looks something like this. This second function we know is a parabola. Shifted up 2 units, it looks something like this. Now let me ask you, are these two inverse functions? We know that inverse functions, the graphs of inverse functions, are reflected across this diagonal line. Are these two functions reflected across the diagonal? Well, yes and no. These parts surely are, but this part here is not. So really, this part should not be a part of this graph. So if we could somehow get a function to look like this, these are graphs of inverse functions. So this answer here is partly correct. There's more to the story. It's like saying, hey, the function is x squared plus 2, but not for the entire parabola, but only for the parabola when x values are greater than 0. And you might say, well, can they be equal to 0? Well, let's think about this. If we put, let's see here, can we have, in this case, it would be a y value equal to 0? Sure, square root of 0 is equal to 0, so we can say equal as well. So if we write our function in this way, so here's your inverse, but only for these x values, then yes, these are inverse functions. So we have to be careful with these. If we just follow the algebraic steps, we get an answer that appears to be correct. If we take a look at our graph, though, we see that this graph gives us too much information. Okay, I have one last idea to share with you. This class here, of course, is called Precalculus, so we're going to see calculus ideas throughout. And you may have friends who are in calculus right now. If they're in calculus right now, they're probably learning about something called derivatives. And by the end of this course, we're going to learn about something called derivatives. Second semester calculus, you'll learn about something called an integral. Now, to take a derivative or to find an integral, those are inverse operations. Right now you are thinking you have no idea what these are, but these are the two main parts of calculus, to find derivatives and to find integrals. These are inverse operations, so if you're strong with inverses, that will definitely help you out when it comes time for you to take calculus. Okay, that wraps up these notes. As you know, you have an assignment on this unit, so once you take care of this, take care of the next set of notes. All right, have a great day.